Hi guys, this is Joljigora, and this is my Mousetrap project. Okay, so I'm going to start with the energy stored in my Mousetrap spring. Um, so I did this graph at school and printed it out at school, so I can't show it to you right now, but I'll just describe what I used it for. Okay, so to find the energy in the Mousetrap spring, you just take the area under the graph of your force times distance graph after using the torsion wheel. And I noticed that my graph is just a trapezoid. So um, I just took the area as a trapezoid, so which is 1/2 base 1 time plus base 2 times the height of the trapezoid. So I use Logger Pro to identify the the lower base as 0.8 and the higher base as 3.6, and we know that the height is 0.06 pi. So I multiply that out, and I got 0.415 joules. And then moving on to the my position versus time graph, which is over here. Sorry. Um, I simply used Tracker to take note of my Mousetrap car's movement and then input the data into Logger Pro. And as you can see here, this is when it's not yet moving, and then over here, this is when it's accelerating, speeding up, and then you can see that it starts to slow down right about here before coming to a stop over here. I took the derivative of this graph to plot my velocity graph, my velocity versus time graph. As you can see over here, sorry, the stuff is in the way, so it's all right here. You can see that this is where it speeds up, like over here, and this is where the velocity is pretty stable because it hasn't really gotten moving yet, and this is when it's slowing down. Okay, now moving on to the displacement of my car. So what I did was I just took the statistics for the entire thing, and you can see that it has max and min. So I just took the I just took max the max value, which is 1.342, and subtracted it by the minimum value, which is 0.071, because the max value is its final position and its minimum value is its initial position. So I just subtracted those and got 1.271 meters as my displacement. So moving on to the mass of my Mousetrap car. So over here. Okay, so there are 9.8 newtons stored in every kilogram of mass. So I just calculated my average the average force of my Mousetrap car, and then plugged it into this conversion, and I found that my car is 0.357 kilograms, which makes sense because my car is not heavy. So yeah, that makes sense. And moving on to my maximum velocity and kinetic energy. Okay, so the equation for kinetic energy is 1/2 mass times v squared. So I found that my V max is 1.10 meters per second, and I did that by taking the statistics using Logger Pro of this area right here while it's speeding up. And earlier when I was writing this, I actually forgot the squared, So that's why I crossed this out and fixed this over here. So I multiplied 1/2 times 0.357 kilograms times 1.1 meters per second squared, and I got 0.215985 joules, and that is the kinetic energy of the car when it is moving, when it's at its maximum velocity. So when it's moving the fastest. Now moving on to my force diagrams. So this is a force diagram of my car as it's speeding up. This is its weight, which is just its mass, 3.57, or 0.357 times 9.8. And then the normal force is the same because it's not on an incline and nothing is like holding it up or anything. And then surface friction is actually in this direction because it's speeding up. So this is my this is the sum of my forces. Weight and normal force cancel each other out, and then or they're equal to each other, and then this is friction. The sum of forces is in this direction because it's speeding up in that direction. That's the direction of its acceleration. So that means force is equal to the sum of forces, which means force equals mass times acceleration. To find acceleration, I took the derivative of velocity and took the statistics from here to here, which is when it's speeding up. And then, so I got that the mean acceleration while it's speeding up is 0.6337 meters per second squared. So I just multiplied its mass, 0.357, times 0.6337, the acceleration, and got 0.226231 newtons. And then this is my force diagram for my car when it's slowing down. Weight and normal force are the same, because, and friction is in the opposite direction because now friction is working against the car as it's slowing down. Therefore, the sum of forces is also in the opposite direction because that's also the direction of its acceleration. So I did the same thing using Logger Pro, except I highlighted this section of the graph, and then I got the average to be negative 0.5486 meters per second squared. So then I just multiplied that out again. So 0.357 times negative 0.5486 equals negative 0.19585 newtons. And that's the force of friction for both when speeding up and slowing down. Now moving on to the total force. Okay, so I crossed this out. That's not an underline. I'm sorry, because I worded it wrong. This is the total forces acting on the car, which is so I just subtracted the force on the car as it is speeding up, and then I added it to the sum of the force while it is slowing down, and I got 0.226231 minus 0.19585 equals 0.030381 newtons. And this right here is the total force acting on my car as it speeds up and slows down. And now I'm going to show you my energy diagram. So my energy flow diagram. So I represented my car as this little line and wheels because drawing a Mousetrap car is kind of hard. So this is my first moment in time when elastic is at its max because you're pulling the snapper arm back all the way so that you can give it so it's right before you let go of the snapper arm to propel it forward. So elastic is at its maximum and velocity is at its is 0. And then the system is a Mousetrap car. That's what that's supposed to say. And the second moment in time is when elastic is 0 and when velocity is at its maximum speed, which as we calculated earlier is 1.10 meters per second. So the dissipated energy is going to equal E elastic minus EK, and then I crossed this out because again, when I first did my kinetic energy equation, I forgot to square the velocity. So I just redid it over here and did 0.415 minus 0.215985 equals 0.199015 joules. And that is my energy dissipated. Now all of this stuff I just wrote beforehand because it would have taken a really long time if I hadn't. But yeah, so this is my mousetrap project. Thanks for watching.